So, hello everyone. As part of this neural network sessions or these neural network sessions, we covered quite a bit of ground with respect to understanding the deep learning challenges. And now we are going to look at practical issues and how do we actually address those. And mostly the techniques that we are going to talk now would be related to regularization techniques, right? We'll talk about a lot of regularization techniques and then we'll take this discussion forward. Let me open the mind map and do a quick recap, and then post that we will continue the session. So if you go to 360digitmd.com, if you go to our website, you will find a menu option which is called as mind map. When you click on mind map, you'll have a drop down and you can select AI and deep learning. Click on that. And then here we have all the deep learning challenges and practical issues, right? And these are the various things that we have already spoken about. Yeah, we spoke about this, but I think we need to get into deep learning primer and we'll talk about this here. So we have discussed that we have human brain, and human brain processes the information in a certain manner. And that certain manner in which your human brain processes the information is based on a concept called as compositionality. Okay, compositionality means first you try to learn, maybe if it is images, pixels, very low level details. Slowly and steadily you learn the high level details. That is what compositionality means. And then the initial set of hidden layers, if you have input layer and if you have hidden layers, the initial set of hidden layers will capture low level details. The next set of hidden layers will capture mid-level features. And then the final set of hidden layers will capture high-level details. We've already spoken about these. And then you'll have an output layer. In the output layer, if you're, let me open this. Come up. Okay. If your output variable is continuous, in the final layer or the output layer, you will have a single neuron. If you have discrete, if the output variable is discrete in two categories, you can either have a single neuron or two neurons. And then if you have output variable which is discrete in more than two categories, if you have 10 categories, for example, then in the output layer, you'll have 10 neurons. Then we have also spoken about artificial neuron and the two components that it has. One is the integration function. So within every neuron, you'll have two components. Integration component and activation component. You'll have two components. In integration component, you'll have summation, quadratic function, spherical function, etc. And when it comes to activation component, you have a lot of activation functions which are also called as transfer functions. And majority of these activation functions or transfer functions are non-linear in nature. Except for the linear functions. When you say linear functions, it doesn't do anything, friends. A linear function means you're not going to use any activation. Linear function means you'll not use any activation. Whatever value you get here, you take it. Say the summation has given you 0.8. The same 0.8 will go as an output. So this activation function, if it is linear or identity, it doesn't do anything. It will just take the input, pass it as is. Okay, so and you use this activation function, which is linear or identity, both mean the same. That means you typically do not apply any activation function. When you do that, you get you use that when output variable is continuous. Okay. And you have step functions, variants of that, you have ramp function, you have piecewise linear function, RAIL, rectified linear unit, very widely used in the hidden layers. In the neurons within hidden layers, people usually use RAIL because it gives very good results. Then we also have smooth functions. Usually, when you have output variable which is discrete in two categories, we use either sigmoid or tanh. Okay, you have sigmoid or logistic. You have tanh, which is called as hyperbolic tangent. And then we have a smoothened version of ReLU, which is called as soft plus. We have ALU, exponential linear unit. We have swish, which is a combination of ReLU and sigmoid. And then you have max out as well. And there is also another activation function called as softmax. And we usually use this when your output variable is discrete, categorical, in more than two categories. And when you add all the values of the output layer neurons, you need not get one. That means those are not probability values. The moment you apply softmax on the final layer, output layer, then you get outputs which are all probability values. Okay. And then we have also spoken about optimization algorithms. Backpropagation algorithm will update the weights, and optimization algorithm will reduce the loss or cost or error. We now understand the difference between error function, loss function, and cost function. So that's fine. And then you have batch gradient descent, stochastic gradient descent, SGD, and then you have mini batch SGD, mini batch stochastic gradient descent. Here, we have to give an additional argument, which is called as batch size. And then you have momentum, in which you'll have a parameter called as gamma value. Okay, and then you have Nesterov momentum. Here, there are no additional parameters. Momentum will look at the past gradient, past information, and then it will make amends to the current. Whereas Nesterov momentum will look at both the past as well as the future information. Both the past and also future. When we update, what will be the future? Then we have Adagrad. Until here, all these optimization algorithms have a single weight updation formula. The learning rate, etc., is constant for all the weights. So if you have your neural network like this, you'll have a bunch of weights. For all these weights, the weight updation formula remains the same. However, you have Adagrad, Ada delta, RMS prop, Adam, etc., where for every weight, you have a different formula to update. Okay, every weight will have a different formula to actually update. So you have ADA grad, ADA delta, RMS prop, Adam. And in Adam, you have two parameters, beta 1 and beta 2. So, and we have also already discussed about the finer nuances, finer details of each of these optimization algorithms. Having discussed that, we understand that we need to get into deep learning practical issues. Even before that, another recap is this. If you have your output variable continuous, for model evaluation purpose, the accuracy or error function that you use happen to be any of these. Mean error, mean absolute error or absolute deviation, mean squared error, root mean squared error, mean percentage error, mean absolute percentage error, correlation coefficient, bunch of these. And for optimization, which is used to minimize your loss function or cost function, we use any of these. When your output variable is discrete in two categories, for model evaluation, you use any of these. Confusion matrix or cross table or contingency table. And for optimization, we are binary cross entropy. Here, there are a lot of other alternative loss functions or cost functions. However, cross entropy is more preferred. However, there is no stopping. You can use the other loss functions or cost functions. If your output variable is discrete in more than two categories, for your accuracy or error, you use these. And when it comes to loss function or cost function, you use categorical cross entropy. Okay. And the activation function in the output layer would be softmax. This screenshot or this screen that I'm showing you answers a lot of interesting interview questions also. A lot of interviewers, they pick the questions from this particular sheet that you're seeing, right? Because they have a lot of things to be asked. So deep learning practical issues, let us understand this. We will talk about how to avoid overfitting, right? But what is overfitting in the first place, right? If you have data, okay, historical data, and if you're splitting the data into training and test, of course, if you have a bunch of observations, you cannot say that I'm going to build my model on the entire data. Say you have 10,000 observations, right? You cannot say that I'm going to build my model on all the 10,000 observations. Why? Because your customer would ask you on, does it really work? Have you tested the model? If you have tested, what is the accuracy? These kind of questions people ask. Right? They usually ask these kind of questions. So what you do is you first split the data into maybe 80%, 20%, 80% of data into training, 20% into test. Then you'll have certain observations in training, output and inputs, and you'll have certain observations in your test data. After you build your model on the training data, you'll have to test it on the test data, and then you get test accuracy. You also test your model on the training data, and then you get training accuracy. And we are expected to compare these. If the accuracy values are high, how high depends on your business problem. Okay. And if they are close to each other, then you call this as right fit model. Okay, it becomes a right fit model. If your training accuracy is high, however, if your test accuracy is low, if your training accuracy is high and test accuracy is low, this scenario is called as overfitting or variance. Friends, how high an accuracy is better? There is no, thumb rule for this, because your accuracy purely depends on your business problem. If you're trying to solve a business problem pertaining to life sciences healthcare or pertaining to some industry where the data is of good quality, wherein the data is captured, data is captured in a controlled setting, controlled environment, where the chance of you going wrong is very less in terms of capturing the data and storing it. In those kind of scenarios, even an accuracy of 90%, 95%, 98%, you might be really unhappy with, because the data is of very good quality. However, if you're working in the space of social sciences, what do you mean by social science? Maybe some kind of manufacturing, etc., where you cannot be rest assured that the data being captured is of very good quality and it's controlled, to a great extent. In those kind of scenarios, even if you get an accuracy of 70%, you will be very, very happy. So it really depends on the business problem that you're trying to handle. Okay. Next thing is, if your training accuracy is low, that means your test accuracy also most often than not will be low. If both these accuracy values are low, then it is called as underfitting or bias. Okay, then it's called as underfitting or bias. Okay. When you have overfitting issues, you can solve these issues using regularization techniques. Every algorithm, every machine learning algorithm, predictive modeling technique will have a different set of options, which are called as regularization techniques, which can be applied on your data set. Okay, and then the overfitting issue can be addressed. Underfitting issues are usually solved by getting access to more data. If you get more rows, if you get more columns, issues are fixed. Now, one way of avoiding overfitting is using something called as early stopping. And you have error change criterion and weight change criterion. First, we'll talk about error change criterion. Say you have multiple epochs. One time, if your entire training data passes through your neural network architecture, it is called as one epoch. If all your training samples pass through your network once, it's called as one epoch. And then what happens is, when you keep on increasing the number of epochs, your training accuracy will keep on increasing, will keep on increase. Whereas your test accuracy will increase up to a certain point, and then it will start decreasing. And that point where both your training accuracy and test accuracy increase, until that point, it is fine. But if you increase the number of epochs beyond this point, this might be, say 100 epochs. If you make 110 epochs, 120 epochs, etc., then as and how your epochs increase, your training accuracy will increase, but your test accuracy will start decreasing. Okay, your test accuracy will start decreasing. This zone is called as overfitting zone, this entire zone. And the any number of epochs more than 100, if at 100 you're having this right fit, then this zone, entire zone, is called as overfitting. If you increase the number of epochs beyond this point. But if you train your model for less number of epochs, less than 100, then it is called as underfitting. This zone is called as underfitting. So on one side you have underfitting, on another side you have overfitting. Okay. Now let's talk about error change criteria. Say you are training for X number of epochs, epoch 1, epoch 2, epoch 3, E stands for say epoch, or you might think otherwise it's error. Epoch 1, epoch 2, epoch 3, so on and so forth. Say you have 10 epochs, 11 epochs, 12 epochs. In that way, you have the data. Error change criterion means stop when error isn't dropping over a window. You define that window. Say you define, for example, 10 epochs. Example only. You can increase the number of epochs, decrease. Whatever window you want to choose is up to you. Then what happens is, you look at your error value at say epoch 1. And you also look at your error value at epoch 10. So at epoch 1, look at what is the error that you have. At epoch 10, look at what is the error that you have. If the error is not changing beyond a point, you might say that I always want, if another epoch has to run, then I want the error rate to reduce by say 0.1% at least. Epoch after epoch, if your error values reduce, error rate reduces by 0.1%, you want to proceed further, or 1%, let me put 1% just for your understanding. Okay. Say here error was 10%. After 10 epochs, when you observe, error was say 8%. That means 2% reduction. What is the condition that you put? If the error rate decreases by 1% in a window of 10 epochs, continue running. Then say the second epoch, error percentage was 9.9%. And say in the 11th epoch, the error rate was okay, no, let me put it this way. Say it was 8.8%. And here, say it was 7.9%. What is the difference? There are 10 epochs. Difference, 10 epochs window you are looking at. From second epoch to 11th epoch, there will be 10 epochs. From first to 10th, you'll have 10 epochs. From second to 11th, you'll have again 10 epochs. from 3rd to 12th, you'll have 10 epochs. So always the window will be 10 epochs. So here, if you look at these two, the difference is 2%. But if you look at these two, the difference is only 0.9%, less than 1%. And what is your condition? Only if the error rate reduces by more than 1%, greater than or equal to 1%, only then continue running your algorithm. Otherwise, stop. Right? That is what we are saying. And here, since it is 0.9%, which is not greater than 1%, your algorithm should stop. That is called as early stopping. But usually what people also do is, if the error change in the window of 10 epochs, 10 epochs, right? If the error change is less than 1%, then what you do is, you train for a fixed number of epochs after this criteria is reached by lowering the learning rate. So you'll have some meta value, right? If you have chosen default value as 0.01, maybe you'll reduce it 0.001 and you'll run it for another, say, 5 or 6 epochs, say 5 epochs. And after 5 epochs, you stop. This is an optional thing, okay? Usually you stop when the error change percentage is less than your condition. If you put a condition that from, in window width of 10 epochs, we want the error change rate to be more than 1%. Then that 1% is something that we define. It is empirical. It is experimental. It's a hyperparameter, right? To keep changing it, keep experimenting. Okay. There's another option wherein if the error change percentage in a window of, say, 10 epochs is less than 1%, then rather than immediately stopping it, what you also might want to do is, you might want to run it for another 5 epochs and then stop. So again, that is up to you on how you want to experiment, what you want to experiment. Then you also have something called as weight change criterion. Okay, now, say you have a neural network where you have an architecture like this. 1 weight, 2 weights, 3, 4, 5, 6, 7, 8. And then you have to, say you have 8 weights. Then again take 10 epochs. Epoch 1, epoch 2, epoch 10, epoch 11, epoch 12, etc. And you have weights for each epoch. I'm not considering bias. Okay. If you also consider bias, you'll have one bias here, and that will have weights 1, 2. You'll also have one bias here, which will also have another weight. Bias is also weight, right? So 1, 2, 3 additional weights you get. If you include bias, then you'll have 11 weights, including bias. Okay, so including bias, you'll have 11 weights. And here all the weights are, if I were to include bias also, you'll have bias 1, 2, 3. 3 bias, right? 1, 2, 3. Then you'll have weights W1, W2, W3, all the way until 8 weights. So overall you have 11 8 weights. So for this also you'll have 11 weights. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, all these three bias, and you'll have all the weights. In that way, for all epochs, you'll have. Say for 10th epoch also, V1, V2, V3, W1, W2, until W8. And for this also, you'll have so on and so forth. So now, if you look at the difference in the weights, and you put a condition, maybe the condition is 0.1. It's up to you again what you give. Neural networks, deep learning is more of experiments. Okay. So here, if you take epoch 1 and epoch 10, subtract B1 from this B1, B2 from this B2, B3 from B3, W1 from W1. I mean, the weights here and the weights here will be different. When you subtract all these weights from all the corresponding weights here, and when you take the maximum difference, say if you subtract these two, you got 0.01, sorry, 0.2. When you subtracted B2 and B3, say you got 0.18. Then when you subtract these two, I mean B3 and B3, you got 0.17. Then when you subtract W1 and W2, maybe you got 0.31. In that way, when you keep subtracting the weights, corresponding weights, you'll get different values, differences. Out of all these, you pick the maximum value. Say the maximum value is 0.31. Only if this maximum value is less than your condition, you stop training. That means weights are not getting updated significantly. Why do you want to even continue? Right? So say on similar lines, when you go to epoch 2 and epoch 11, when you subtract B1, B2 from B2, B3 from B3, W1 from W1, so on and so forth, you get different values. Say you got 0.08, right? 0.01, 0.07, right? 0.09, so on and so forth. When you looked at the maximum value out of all these, say you got maximum value as 0.09, this one. Is the maximum value less than the threshold that you have given? Yes. So your learning has to stop. Your training has to automatically stop. This is called as early stopping. Okay. Rather than just looking at a number, you can also put conditions such as percentage. If the weight change, if the maximum weight change is less than some 1%, then stop. Do not train it any further. Yeah, this is what is called as weight change criteria. This is one technique to avoid overfitting. Any technique which is used to avoid overfitting is called as regularization technique. So any technique which is used to avoid overfitting is called as regularization technique. Okay. Any technique which is used to avoid overfitting is called as regularization technique. Then you have dropout. And then you have also drop connect. So let me first explain dropout, okay, and then we'll get into drop connect. In dropout, what happens is you'll have two phases, right? You'll have training and test. whenever you're building your model, you'll have training where you train your model, and then on the test data, you test. That's what happens to you. And if this is a network, this is your input layer, this is one hidden layer, this is one hidden layer, and you have one output layer in which you have a single neuron. If every neuron is connected to every other neuron, then what is it called as? What is that network called as? That network is called as multi-layered perceptron or dense network or fully connected network, right? All these are different names given, or artificial, you can also call it as artificial. These are the various names given to the network. For each hidden layer, for each training sample, if your data set is like this, you have 5, right? So you have your output 1, 2, 3, 4, 5, and then you have all the various inputs. You have, say, 10,000 observations. For each hidden layer, you have one hidden layer here, another hidden layer here. For every training sample, if you take one, so for each training sample and for every iteration, iteration means you update the bits. You actually ignore or zero out a random fraction of nodes. Right? What does that mean? A random fraction of nodes, you zero it. So it's very, very interesting thing. Just you will have to focus a bit, and you'll be able to understand more. So just a minute, sorry. Okay. So if you put this random fraction here as, say, 50%, 0.5, or 50%, when you do that, 50% of nodes or neurons will basically become 0. Okay. So what you do is, if you have this neuron or these neurons, right, assuming that this is also a hidden layer, assume that this is also a hidden layer. Okay. For now, assume this is also a hidden layer. So hidden layer 1, hidden layer 2, hidden layer 3, and then output layer. Say you also have one input layer, which is not demonstrated here. Then what we do is, we randomly select 50% of neurons from the hidden layers, and then we make their activation 0. Suppose you have a neuron here. I'll ensure that the output, because every neuron has what? Integration and activation. Okay, I'll draw it like this. It'll be easy. Say you have one input layer. Say you have a hidden layer, and then you have, say, output layer. Okay, let me draw the connections. Then, in that case, I think I also need to add one more, just to ensure that the 50% thing is supported. Okay. Now, if you say that for every row, if you're passing this row to your network, then randomly 50% of the neurons from your hidden layer are gone. So assume that this is your input layer, and this is your hidden layer, and then this is your output layer. So what you do is randomly 50%. So say this and this, you will have integration, activation, integration, activation, integration, activation, integration, and activation. Say randomly for these two neurons, this neuron and this neuron, randomly, you make the activation as 0. When you make the activation as 0, what will happen? The output that this neuron gives to this and this is gone. And the output this neuron gives to these two is also gone. And you're training your model. Okay, because these two neurons were randomly selected and they are ignored. I mean, their activations are made 0. So you are clamping the output to become 0. The moment you make it 0, any connection that it gives, it will become meaningless because anyways the values here are 0. This is for one example. For another training example, for instance, what happens is, say, come on. Okay. So when you pass on the next set of inputs to your network, you once again randomly choose two neurons. This time, maybe this neuron and this neuron got selected, assume. So what happens is the output, the activation function value is clamped to 0. When it becomes 0, all the connections are removed because output won't go here, the output won't go here, this output doesn't go here, this output doesn't go there. This is how it works. Dropout. And this happens to be a very good regularization technique. However, when it comes to testing, we use all the activations, but reduce them by a factor of 50%. Okay, once again, you use all the activations, but just you reduce them by 50%. Meaning what? You'll have connection here. You'll have a connection like this. You'll have a connection like this. All the connections would be there. And what you do is, all the activations, you reduce them. Means whatever value you get here, whatever value you get here, here. If you got a value of 0.8 here and 2.6 here, then 3.2, then 1.8, whatever. If you make it half, this becomes 0.9. If you make this half, this becomes 0.6. If you make this half, it becomes 1.2. If you make this half, it becomes 0.4. So use all the activations, but reduce all of these by a factor 0.5. Okay, that's it. That's how it works. Okay, that is how your dropout works. It happens to be a very good regularization technique. Next, we also have something called as drop connect. Everything is similar to dropout, but the only difference with respect to drop connect is that instead of making the activations 0, we disable the weights itself, set the weights to 0. So what happens? A neuron, you're not making the output of this 0. If you make the output of the 0 of this, all 3 connections will be gone. But what are we doing? We're just making a few weights 0. So the value which goes here will become 0. The value which goes here will become 0. So those weights only are ignored. If you make this node 0, all the 3 connections are gone. But here what is happening in drop connect? Only the connections are being dropped. Only the connections are being dropped. So that way one connection from this node will still be there. Okay, that is the difference. Usually people use dropout. Drop connect, not many people use because it's not giving you good result. But from interview standpoint, people might ask. So it's always better to be prepared for the worst. Then you have noise. You have something called as data noise, label noise, gradient noise, etc. Data noise means you take your data, say you have your output variable. This output variable usually is also called as label. And say you have inputs, x1, x2, x3. So this is age, 32, 36 in that way. Gender, male, female, and then you have say income, $1,000, $8,000, etc. Data noise means you randomly add some noise to these. For example, you might say that what I'll do is if I have say 1,000 observations, I'm going to create another 1,000 observations, 1,100, 2,000. And for these next set of 1,000 observations, okay, for these next set of 1,000 observations, I'm going to add, say, number one, to all these values. If you add 1 to this, it becomes 33. If you add 1 to this, it becomes 37. Say third person's age is 43. If you add 1 to it, it becomes 44, so on and so forth. Wherever you have continuous values, that is what you do. Maybe you add 10 to this, or 100 or 1,000 to this, it becomes 11,000. Add 1,000 to this, it becomes 9,000. Add or subtract some numbers. This is just adding some additional noise. Okay, you're just adding some noise to your existing data. This also happens to be a very good regularization technique, which will help you avoid overfitting. All these early stopping, dropout, drop connect, noise, all these will help you reduce the they will help you get out of this problem called as overfitting. If you have categorical data, you flip it. If you have male, make it female. If you have a female, make it male. Flip it. Label noise also is the same, friends. But label noise is, instead of doing that for the inputs, you do it for the output. You just flip. If it is person will default, not default, not default, default in that way, then you flip it. Wherever you have not default, default, make it not default. Wherever you have not default, make it default. Default would become not in that. Okay, and if the output variable is continuous, say you're trying to predict salaries of people. If you're trying to predict salaries of people, I mean, income is anyways there, what should I say? Say loan interest amount, 8%, 9%, 7.2% in that way. Just maybe add or delete some numbers. Say You subtract 0.1 from this, it becomes 7.9%. This becomes 8.9%. This becomes 7.1% if you subtract 1%. So you do some math operation to bring in some noise into your data. Then you also have something called as gradient noise. Updating the weights. Gradient is nothing but rate of change. If you have an error surface like this, you update the weights, you reduce the loss. Okay, again you update the weights, again you reduce the loss. You continue in that. But updating the weights means you're trying to find what will be the rate of change. From this point to this point, what will be the rate of change? That is gradient. Gradient or rate of change. And this rate of change or gradient is found using derivatives, calculus. Once you get that gradient value or rate of change or derivative, add some noise to it. Take your gradient value using your normal distribution. This is called as Z normal distribution, right? Standard normal distribution or Z distribution, wherein mean will be 0 and standard deviation will be 1. But here standard deviation is written as, variance. Square means variance. Variance is written as eta value divided by 1 plus the time period, gamma. Time means first epoch, second epoch, third epoch, whichever is the epoch, that value you put here. And then the gamma is a scaling factor. Whatever value you get here, generate a normal distribution with mean 0 and this variance. Randomly take some numbers from that, add it to your gradient. That would give rise to a new gradient value. If you're finding it difficult, forget it. What did I say? I've told you that first time when you listen, if you're able to understand 40% of the things, job done. That is all that is expected. You need not understand 100% of things. But then make a running notes. Otherwise, your brain won't be focused. Either you understand or do not understand, forget it. Keep writing your running notes. Then when you watch the video for the second time, you would be able to understand 60% of the things. Watch it third time, and that's the gold standard. You will cross your 80% barrier, and this is what is needed to clear the interviews. Clearing the interviews and getting data science job is a very simple and straightforward task. It only needs hard work and discipline. Okay. Then there are a bunch of other things such as data transformation. You have something called as batch normalization, shuffling the inputs, curriculum learning, data augmentation, bunch of things. So let us understand all of these things. Yeah, done. We have only 1, 2, 3. 3 slides and done. And then we'll get into the practical aspects of it. So let's spend some time on this. Okay. So when it comes to data transformation, when you have your data, say you have a variable called as income. If you have income, you just take log of income and that creates another column. So drop this you remove this column income and include log of income. Okay, include log of income in your analysis. That's data transformation. Then you have an input, you have a technique called as shuffling your inputs. So shuffling your inputs means If you have a neural network like this, okay, what you do is, and say you have all your observations here, 1,000 observations, and you have, say, 3 inputs. So you have an output, you have input 1, input 1. So what you do is, basically, this will be x1, x2, x3. Next time, what you do is, this neuron send x2 here, x1 to this, and x3. Next, what you do is send your x3 here, x2 here, x1 here. Shuffle your inputs in that way. This also happens to be a very good regularizer because each time you shuffle, there will be different weights that your inputs will be getting multiplied with. This also happens to be a very good regularization technique. Then you have something called as batch normalization. What happens in batch normalization? Say you have your output variable and different input variables. And say you have 1,000 observations. And assume that you have chosen a batch size value to be 100. If the batch size value is 100, 1 to 100 will be one batch. 101 to 200 will be another batch. 201 to 300 will be another batch, so on and so forth. You'll have different batches of data. Take this batch. Okay. And take all the values, say, I'm thinking out aloud on how do I explain you guys. Okay. Take all the weights. You'll have weights. Okay, all the parameters, like you'll have bias. Let me call that bias as gamma maybe. And let me call all these weights as beta values, beta 1, beta 2, beta 3, in that. So take all these weights, take an average of all the weights, and take a standard deviation of all those weights, or variance of all those weights, and then normalize it. How do you normalize? Each value is equal to x, the weight value minus mean of that divided by standard deviation. That's what is given. Square root of variance is nothing but standard deviation. And when you do this, you get new set of weights. This will ensure that all the weights are always in the range of, or all these weights are in a specific range such that mean equal to 0 and standard deviation equal to 1. You all are already aware of transformation, Z transformation, normalization, standardization. Already you guys are aware of it. And that's the same thing that is being done here. Normalization, batch normalization. The only thing that you do is for every batch, when you pass, whatever weights you get, take those and then you can normalize that. That is called as batch normalization. So you understand all of these now. And batch normalization is usually applied in between your fully connected layer and your activation function. That's where you give your batch now, usually. Fine. Next thing is data augmentation. But I think we already spent some good amount of time until now. So let us take a quick break and then we'll get started. So let me So let us talk about data augmentation, which is usually associated with images. But even if you have the regular columnar data or tabular data would mean the same. Then you try to augment the data. But here, as part of our data augmentation, you take the images, and if you have less images, for example, when we have built cancer prediction model, we had to deal with radiology images and pathology images. Usually what happens is you'll have very less number of images, very less. Handful of images is what we'll have. Okay, when it comes to life sciences healthcare. And we had access to only 3,000 images. And if you have access to only 3,000 images, okay. And if you want to train your model, you can use manual way of extracting the features. Manually, you can extract all the features. And then you can apply traditional machine learning algorithms on that. So you'll have an option to manually extract the features and then apply traditional machine learning algorithms on that. However, if you want to apply deep learning, you need more images. Whenever you want to apply deep learning algorithms, you need to get access to a lot of data. How would you get access to a lot of data? Through augmentation. Okay. So if you want to apply deep learning algorithms, then you need more data. When will you get access to more data? You'll get access to more data when you perform data augmentation. What you do is, as part of data augmentation, if at all you have color images, flip the colors. Any color image, this is the original photo, any color image will have red channel, green channel, and blue channel. It is called as RGB image, right? You flip green into red, and red into green. You're flipping the colors. Or you replace green with red channel. Replace blue with also red channel. Or replace green with blue channel. When you do all these permutations, combinations, just imagine what will happen. If you have, say, 3,000 images of radiology or pathology, and then these are all in the format RGB. What you do is you replace green with red, RRB. Then you will get another 3,000 images. Then RG, instead of blue, put R. Then you will get another 3,000 images. Okay. Then RRR, all red channels. Then you will get another 3,000 images. Just imagine all those combinations. Instead of green, instead of red, replace it with green. Replace blue with green. So you'll have huge number of images. Then you can also do something called as translation. If this person is here, in the image, if the person is here, then translate. Ensure that the person comes somewhere here at the center maybe. So you're translating the image. You rotate the image. If the person is here like this, rotate the person like this. Rotate the person the other way. Rotate it by 10 degrees, 20 degrees, 30 degrees, 40 degrees clockwise. Rotate the image 10 degrees, 20 degrees, 30 degrees, 40 degrees, anti-clockwise. If you keep adding all those images which are translated, rotated with different degrees, then eventually you will have humongous database. And then you can apply deep learning algorithms on them, because deep learning expects us to have huge amount of data. Only then can we train the model. Okay. Then we have something called as scaling. Scaling means reduce the size of the images. If the image is like this, reduce. You can reduce the height, or you can reduce the width, or you can reduce both, so on and so forth. And then you also have affine transformation. If the image is like this, you make it like this. You translate it. You make it like a rhombus. I mean, these are all the various techniques, and data augmentation happens to be an amazing regularization technique when you deal with images. So remember, if you have images, and if you're handling image kind of a problem, just do one thing, do regularization. That's it. Don't worry anything about anything else, right? Just perform regularization. Job done. If you perform regularization, it will serve as, I mean, if you perform data augmentation, it will serve as an amazing regularization technique. Then weights. Weights or parameters or coefficient values all mean the same, right? All mean the same. And usually weights are, how are weights assigned? Randomly. Randomly, the weights are assigned. So, okay. While weights are randomly assigned, and this is considered to be one of the best ways of starting your model training. When the model training starts, it is going to randomly assign the weights. And this is considered to be the best way, right? The best way to get started. However, there are other weight initialization techniques, such as Xavius initialization. When it comes to Xavius initialization, we use uniform distribution. Uniform distribution means, okay, first of all, let me draw normal distribution like this. In normal distribution, the probability of getting very low values or very high values is less. On y-axis, if I have probabilities, the probability would be very less. Right? The chance of getting the values from this central portion would be very high. The probability is going to be very high. Okay. If you want to choose weights in this region. However, when it comes to uniform distribution, this is how it appears. The probability of choosing weights here or in the central region is all the same. So the probability of choosing weights across when it comes to uniform distribution is the same. Okay, this is something that we need to remember. Next, we have something called as Xavius initialization. In Xavius initialization, you have fan in and fan out. For instance, say you take this neuron as an example. How many weights do we have? 1, 2, 3. Or let me take rather this neuron as an example. Okay, this one. If you take this neuron as an example, how many outputs are there? 2. So you have how many fan outs? 2. How many inputs are there? 1, 2, 3, 4. So number of fan in equal to 4. You have 4 fan ins and 2 fan outs. Okay, so 4 fan ins and 2 fan outs. So in the uniform distribution, you write it as minus square root of 6 divided by square root of fan ins are 4 plus fan outs are 2, comma square root of 6 divided by fan ins are 4 square root of 4 plus fan outs are 2. So this would be written as minus square root of 6 by square root of 6, comma square root of 6 by square root of 6. So minus 1 comma 1. All the weights will be randomly initialized from this range. One is randomly initialize the weights. I mean, randomly when you choose weights, you can choose any weights between minus infinity to plus infinity. Any weights. However, when we use Xavius initialization, when the weights are initialized, they get initialized from the range of minus 1 to plus 1. And Caffe, you have Caffe, which is a deep learning library. When you initialize the weights using Caffe, it is a small variant of Xavier's initialization. And here it will be minus 2 divided by fan ins and fan out. So you have, if you take this same neuron, you'll have 4 fan ins and 2 fan outs, comma 2 by again 4 fan ins and 2 fan outs. So it'll be minus 2 by 6, comma 2 by 6. So it is equivalent to 1 minus 1 by 3, comma 1 by 3. If you use something called as He's initialization, it has again a different formula to calculate. The point that I'm trying to drive is why you have random weight initialization. There are also other techniques for initializing the weights. Initializing the weights is very, very important. If you are able to initialize the weights better, you get better accuracy. But when people experimented immensely, they figured out that these initializations were not giving very good result in comparison to random initialization. In comparison to random initialization, these other techniques weren't giving very good result. It was giving good result, but not exceptional result. Okay, that's this part. Okay. So things that we need to remember, all of these, Here are a few standard techniques. You use mini batch SGD with Nestro momentum or mini batch SGD with Adagrad or RMS prop or Adam. ReLU, leaky ReLU, max out happen to be the best bets for activation functions. Then you have batch normalization. Batch norm techniques are here to stay. Right? Then you have dropout, which happens to be an excellent regularization technique. Then you also have drop connect and a bunch of other techniques that we have spoken about, like batch normalization, right? Transformation, shuffling the inputs, adding noise, data noise, label noise, gradient noise. All these are amazing techniques. Data augmentation, certainly when you have vision related problems that you're trying to solve, this happens to be a very good technique. Then you have weight initialization. While randomly initializing the weights will give you amazing result, there are also the other techniques such as Xavier's, cafes, variant, He's initialization, all that. When you have all these weapons in your hand, it's all about going ahead and implementing, right? Practically implementing the solutions. So let us now venture into the practical aspects of it and try to practically understand how to handle using TensorFlow Keras. I would combine these two ways, TensorFlow and Keras, because even if you write using Keras, the code gets executed in TensorFlow. Doesn't matter, right? Nowadays, you have very powerful computers, so that small difference of training time doesn't really warrant you to write TensorFlow code. If you write TensorFlow code, you end up writing a lot of lines of code, which only the core, adroit programmers would understand. What is the use, right? Business users also should be able to understand the code that you're writing. And you should also be able to accomplish the task. So that's what is happening here. Okay, let's not waste too much of time. Let me go to the learning management system. And let me get into this. This is a username and password for the admins to log in. Everything would be visible, all the stuff would be available. I'll go here and ways this. So here I need to download Python code part. Let me download it. And I think these two training set. Unzip these. Let me unzip this. And let me unzip this. And one more very, very important thing is, friends, your mind map. All that we have spoken about would be in this. Okay. What are the various options for deciding the best neural network settings, right? You need to figure out number of hidden layers. It's a hyperparameter. Number of neurons in the hidden layer. Which activation function should be used? What is the error function or cost function or error loss function that we need to use? I think this has to be lost. What gradient descent algorithm do you want to use? What should be the mini batch size? How many iterations do you want to run? How many epochs do you want to run? Right? What are the various eta learning rate values? Learning rate eta values range between 0 to 1. Fixed learning rate has this issue of bouncing around the ball. Hence, you have shrinking learning rate. Shrinking learning rate includes, this is also called as a decay parameter. Okay, it's also called as a decay parameter. Decay means reducing, right? In that way, shrinking also means reducing. You have exponential shrinking learning rate, delayed exponential, bold driver, step, all of these. Then you have weight initialization, in which you have random initialization. Glorot Xavier is a person, so a few people call it as Xavius Initialization, a few people call it as Glorot. Then you have He's initialization, then from a normal distribution, randomly generate weights, or from uniform distribution, generate the weights randomly. Then we have encountered vanishing gradient and exploding gradient problems. This issue can be addressed by batch normalization. If you use batch normalization, you overcome the issues of exploding gradient or vanishing gradient. Then you have overfitting issues, right? And there are a lot of regularization techniques which help you address. All the techniques that we have spoken about are clearly listed down here. Okay. Couple other things that I think we skipped. Covariate shift and correlation between inputs. When the inputs are correlated, and when you build a model, not just deep learning or neural network model, any model for that case, it doesn't give you good results. So you have to decorrelate. To decorrelate, people usually use, techniques such as correlation, principal component analysis. Principal component analysis will ensure that if you have inputs which are correlated, okay, it will make it uncorrelated. Then you have something called as covariate shift. Covariate shift means, say, if you have an output variable, okay, if you have an output variable, which is salary, you're predicting salary of people who undergo data science training. You're looking at their years of experience, graduation, and say some other gender maybe, and then you're trying to figure out what will be the salary. And salary, when you have trained your model, was say following normal distribution. So the training data, say, was following a normal distribution. But then when you try, say you built a model, and when you try to test it on the test data, say the distribution was appearing like this, skewed. Okay, say the data distribution was skewed. So your model doesn't work well. You're training the model on different data set, and you're testing it on a different data set. So it doesn't work well. You need to ensure that your training data and test data have the same data distributions. Same is the case with inputs also. Look at the data distribution of all of your inputs. And your training data also should have more or less the same distribution. If not, it is called as data drift. Your data is drifting. The moment your data drifts, you'll experience model drift. Model drift means your accuracy will go down. Accuracy reduces. It's something like you prepared for your exam on mathematics, but you started getting questions from science, physics. Obviously, you'll not be able to do a good job, right? So that is what it means, data drift. If that is the case, what will happen to the marks? You'd obviously get less marks. That is called as model drift, right? If your accuracy reduces. If your output variable is not continuous, if it is discrete, okay, if your output variable is discrete, then what happens is, say, you have default, not default, not default, default. In that way, you have the data. Okay. Then you'll have default. Number of default cases are, say, only 10%. Non-default cases are 90%. On this data, you trained your model. But when you test, say the data changes. Now, maybe default is like this and not default is like that. Meaning, not default, say you have 30%, and not default, say you have 70%. Say this is your test data. So obviously, the model, when you train, had a different distribution. The distribution of default and non-default is 10-90%. But on your test data, it was like this. So it doesn't work well. Once again, the same thing. You prepared for maths exam, but in the exam hall, it was actually physics. So obviously, complete data is different, and then obviously the results also will be very different. Okay. Now, the practical aspects. What do I do? How do I run the model is what I'm thinking. Let's do one thing. Let me go to Google Colab. Or let me do one thing. I'll use 3 or 4 rather, right? Let me use first Spider, which is an integrated development environment, IDE. We'll first use Spider and build a model. And then I'll also use Jupyter to build the model. And then I'll use Google Colab to build another model. Of course, you have Amazon SageMaker Studio Lab. That is also something that you can explore. All these are different IDEs, friends, like Uber, Ola, and in ASEAN market, there is something called as Grab. These are all cabs, taxi hailing services. Either you take Uber or Ola or some other cab, ultimately you'll reach the same destination. Wherever you want to go, you can go either using Uber or Ola or anything. It doesn't matter. If you want to watch videos, either you can watch the videos on Windows machine or you can use it on MacBook. Doesn't matter, right? It's like that. So it's up to you on what you want to use. But anyway, I'll open Anaconda. Anaconda Navigator. Let me open that. And we'll quickly do the practical stuff. After this, I'm also going to get into Pytorch. And then I'll not, okay, we'll also have CNN and RNN. Obviously, I cannot get into very thorough depth of that. Whatever is needed for the data science training, I'm going to explain those things. But your artificial intelligence part, which is part of professional certificate program in data science and AI, there it will get into the very core depth. That depth, I'm not going to cover. Until now, I covered when it comes to all the basics. But that amount of depth, we will not be covering when it comes to the practical aspects. Okay, I'm just cautioning you this because there you learn about various other things, additional things. I'll talk about what are the additional things that you will learn later. Okay, now. So let me launch Spider. While it launches. Okay, I'll be in the downloads folder. Let me open the code. Friends, if you want to learn Python programming, if you copy this code, paste it and run each line, you will not learn Python programming in your entire life. If you want to learn Python programming, you need to type it. For example, say it is written as import numpy as np. Go here, type it. Import numpy as np. And click on this run. It would execute the line. You need to keep typing each line of code right from day one until the time you get a job. If you're looking out for a job, right? Until then, keep typing. If you don't type, you'll not learn. You might see that line of code called numpy, import numpy as np. Even if you watch it 1,000 times, you'll not learn. You need to type. Only if you type, you will learn. Please, please bear this, register in your mind. Even today, it is not late. If you are a person who has been just copying the lines of code like this, pasting it here and then running, then you'll not learn in your entire lifetime. When will you learn? Only when you type it, right? For example, this line of code, you should have typed it like keras.models import sequential. Only if you run, you will learn. Otherwise, you will not learn. And have no doubt about that. Here, there is some Cuda library and all that which is missing. I don't really care about those things. Let's see if it throws any error, I'll resort to Google Collab and do it. Because for your deep learning models to run, your deep learning models run on GPUs. To install GPU on your local computer, if you have a GPU and if you want to install and ensure that your code is accessing GPUs, then you need to have Cuda. There's something called as Cuda. Then DNN, CDNN, and then you need to install. I think these two should do. And then, of course, you need to install TensorFlow or Keras, etc. Here it says Cuda something version 11, DLL error, and all that. Okay, let me do one thing. To avoid that issue, do I have a GPU? Yes, I have a GPU. How do I make out whether I have a GPU or not? I'll just say, I think it won't be visible. So let me go to start here and then type task manager. Okay, let me open task manager. And here, when you go to performance, you will see GPUs. Not this GPU, not Intel thing, which is graphics related, doesn't run your deep learning models, right? You need to run NVIDIA GTX 1660 Ti. You need to run this. Okay. And what is the temperature is also coming up. 58 degrees Celsius is what it is experiencing, despite I switching on the AC and all that. And I have 8 GB approximately GPU memory, right? Okay. Otherwise, on my computer, it is 16 GB. Your GPUs also will have some. Now I'll go to environment. I'll go here, say open terminal, and then I'll say Conda install TensorFlow GPU. Not pip install, Conda install. What Anaconda does is it will get hold of different Cuda versions, CDNN versions, and then it will install. So let's do this. That's I think CUDNN, not Cuda. So let me go to program files. We have NVIDIA GPU. Yes, Cuda is there. Version this. Yeah, CUDNN. CUDNN. There is some configuration that you need to do. That CUDNN you need to copy and paste from a different location into this, etc. So what is it doing? The following packages are causing the inconsistency. Okay, all of these versions, the different versions for that case. It is trying to it will fix it automatically. So let's see. Let's wait and see and how it's going to fix it. Usually pip install will install the other libraries, but then if you actually need the right version which makes use of GPUs, then it actually makes sense for us to use this Kunda install. If you use Anaconda only, it works obviously. It will kind of try to resolve your environment. Let's see what it has to do now. Let's figure out that there are certain inconsistencies, hence the GPU version doesn't work. Hopefully it will start working now. Let me pause the recording until then. So I think this process would take a while. What we shall do is I shall minimize this and we shall resort to Google Collab and continue our work. So Google Collab, you just need a Gmail account to be able to log into Google Collab and you just click new notebook. That would open a new notebook for us. And there we can do this. So there we go, we have it here. So let me call it as ANN or NLP. Okay, and I would click on runtime and click on change runtime type. Right. Here we shall select GPU. Even on the free versions, you'll have GPU. While I'm using Google Colab Pro, there's also Pro Plus, but I'm using Google Colab Pro. I don't know who your brother is. Apple save. I don't know why it got enabled. Anyways, I'll click on save. And since I'm using Collab Pro, when I click on change runtime type, I also have an option to choose high RAM. Let me see. Let me click on connect. But even if you work on the regular thing, right? Regular Google Collab, it works. It doesn't throw any issues as such. So it has initialized and assigned some RAM for us. If I hover my mouse, it has assigned 25 GB RAM and 166 GB disk, that is storage. So I'll just copy the required libraries. Anything which we write after hash is a comment. So I'll click on run. It will load because TensorFlow is from Google, right? So Google has already pre-installed on Google Colab a lot of important libraries required for machine learning purpose. Even Pytorch, I believe it's pre-installed in Google Colab. But anyways, let's try out. When I click on, when I hover my mouse on this block of code, you'll have a plus sign click on that. Then you have an option to set the random seed. Then you have these options. Okay, but then where are these data sets? Right, where are these data sets? So I'll click on this. I'll click on this option, which will mount a Google Drive. I'll say connect to Google Drive. It's mounting the Google Drive. Sometimes it will ask you to authenticate. You can also authenticate, and it works. Okay, Google Drive is mounted. I'll go here. Let me do one thing. Let me create a folder. That would be better. Okay, let's create a new folder. I'll name it as ANN MLP. And then when you refresh it, come on. Why is it not getting renamed? Strange. Do we have another file with the same name? Let's see. Rename as ANN. Now it got renamed. So I'll get into this folder and then say upload. And we are going to upload these two files. One is training sample. It's still getting uploaded. Not sure, it should not take so much time. It's a small file for that case. It's getting uploaded if you see here. Not sure why on earth is it taking so much time. Okay, what is the status of this here? Yeah, it's still examining the conflicts. Let it do that, and this file has to be uploaded. While that happens, let me upload into this the test sample also. Test sample is also going to be uploaded. Yeah. So we have both training and test sample. Then you need to click on this, copy the path, and paste it here. Go to test data. Just click on the three dots that appear. Click on copy path. Paste it here. That's it. It's pretty simple, straightforward. So what are we doing? We are importing all the important libraries. We are setting the seed to ensure that the training data and test data, each time when you train your model, it gives you the same results, same training and test data. Then using, we are importing pandas, and when we say pandas.read_csv, you can read the training sample and test sample. Let me run it. Done. When you see a tick mark there, green tick mark, that means it got executed in 0 seconds. I mean, less than a second. When I have my mouse on that, it says here is the plus sign. Let me click on that. Go here. And we are going to do something interesting. So let me explain what's happening here. You're going to training data set. You're storing this train sample CSV file in training, test sample CSV file and test. Train.index location. I location means index location. You have square brackets. You have rows and columns. The first part contains rows. The second part contains columns. If you have a colon and that's it, nothing else. If you just have a colon and leave it, that means you want all the rows. Take all rows. When you say 1 colon, that means from index number 1 onwards, you want all the columns. In Python, you'll have this first column has index number 0. This has index number 1, index number 2, index number 3, 4, so on and so forth. This is column number row number 0, row number 1. Index numbers start from 1. So first column is given index number 0, first row is given index number 0. From 1 until end, from 1 until whatever you have, how many you have, take everything. And that would become your training data inputs. And this first column is given a name called as label. The column name is label. So what we are doing here is, if you come to this line, train, go to the training data, go to the column which is named as label, take all the values from that, is what we are saying. Okay. Now, same is the case with test data also. Test index numbers, you're going to test data, you're taking the index numbers, index location. Location means index location. You want all the rows and you want column numbers from 1 until end. 1 until end. Index number 1 until end, you want to take all of that. You want to take all the corresponding values of all those columns. And when it comes to test data, you're saying go to test data label. Label means the output variable. Take all the values corresponding to that and store it in y_test. Alongside that, there is one additional thing that is happening here. If you observe very carefully, we are taking all those values and doing a coercion, typecasting. Typecasting or coercion means forcibly converting one data type into another. So when you load this data set is going to contain, if I am not mistaken, it is the digits data set. So let me open this. So if you look at this, first column name is label. Next it is pixel 0, pixel 1, etc. In that way, how many pixels do we have? 783, but it's starting from pixel 0. So 784. These are all handwritten digits, friends. These are all handwritten digits. Digit 0, digit 1, in that way you'll have handwritten digits. And each and every digit will have pixels. To have pixels. And each pixel value ranges from 0 to 255. 0 means black color and 255 means white color. Okay, 0 means black color, 255 means white color. So all these are numbers, right? All these 0, 1, 2, all these are numbers. And you don't have any decimal values. These are all numbers. So you see some numbers 101 and all that. You don't have decimals here. And when it comes to neural network algorithm, you'll have inputs, neurons. And how many neurons? 784 neurons you have. Because each of that handwritten digit is of size 28 by 28. 28 rows, 28 columns, those many pixels. So you'll have 784 pixel values. And then you'll have some hidden layer, etc. So all these weights are float values. All the weights will be float, of type float. Float means they'll have decimal values. Okay, float means they'll have decimal values. But all these inputs that you have in your data set are nothing but integers. All those are integers. But then you have float values which are decimals. When these integers which are inputs, so all these neurons will have inputs which are integers. But all these weights will be float. When you multiply integer data type with the float data type, it will throw error. You'll get error, some coding programming error. In order to avoid that, what you're doing is, of course, weights you cannot change it to integers because weights are randomly assigned and they can also have decimals. So you have no control on that. The only thing that you can control is the inputs. You can change the data type of inputs. So here what we are doing is, we are taking all those inputs and you're saying that convert the data type of this into float. What is 32 and 64? 32 is 32 bits, 64 is 64 bits. On the latest of the computers, you can use 64 bit also. Just to ensure that you have all sort of backward compatibility. Even if something is of 32 GB, it should be compatible, right? Just to ensure that we are saying float 32. But float means decimals are allowed. So that is what we are doing here, friends. Let me run it. So we have training data and test data. We segregated training data inputs, training data output, test data inputs, test data output. We segregated. Then we changed the type to float. All these are changed to float values. Next, let me add next line of code. And what we are trying to do here is normalization. Why are we doing this? If you look at this data set, you have a column where you have zeros, you have a column where you have 105, you have columns where you have 253, etc. The scale is very different. When the scale of the data is very different, right, like this, you need to normalize the data. If you normalize the data, what is the benefit? Quickly, you will reach the minima. Wherever you have minima, you will reach that minima faster. Okay, that's the advantage if you normalize the data. And that is what we are doing. And here, in order to normalize, we are dividing each pixel value with 255. Already, what did we speak about? Pixel values range from 0 to 255. And if you divide each value with 255, say 0 gets divided by 255. If you do that, you get 0. Here 255 gets divided by 255, then you get 1. So the values now range in between 0 to 1. Earlier, the values were in the range of 0 to 255. So you could normalize it. And in that way, every column, each and every column that you're seeing here, that is each and every input that you're seeing here, will be in the range of 0 to 1. If you look at the range of each and every column, it would be in the range of 0 to 1. So let me run it. Next, again, I'll hover on this line that you see, right? Differentiating between the block of code and the next thing. Just click on plus sign, you get a code. Then what we are doing is, all these are data pre-processing techniques or data preparation techniques. techniques, right? You're preparing your data to build a model. So these are all data preparation techniques. And here what we are doing is, you're taking your output variable and you're converting it into categorical. Means what? One hot encoding basically. And what's happening typically? Right, that would be your question. What is happening actually here? Let's see. In the data set that is given to us, you have a column called as label, which is nothing but output variable. And you have various inputs. How many inputs do you have? Pixel 1, pixel 2, pixel 3 in that way. 784 pixels. We have taken all these inputs. We converted them into float so that when the weights are in float format, if the inputs are in float, when you multiply, you get the good results. Then you are dividing each value with 255 to ensure that you normalize the data. So data pre-processing with respect to inputs is done. Now we are coming to this output. Either this is 0 or 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. We already have discussed about cross entropy. If you remember on what we have done there, we have taken a specific data set and we took an example of animals, images. Say you have cat, dog, tiger, lion. And say you have the actual data set. If they say there is an image of cat, if it's actually cat, you put 1, 0, 0. For cat, maybe these are your actual values. Let me call the actual values as P. Then you have your predicted values here. Let me call that as Q. Say cat is, it's actually cat, and here you got probability as 0.7. There's 0.7 probability that it is cat. 0.1 probability that it is dog. 0.15% probability that it is tiger. 0.05% probability that it is lion. When you add all these numbers, it will sum up to 1. Now, if you want to calculate cross entropy, summation of I equal to 1 until n, minus would be there, pi into log of qi, of course, based. If you, n means 4 classes is what you have, 1 to 4. So if you were to expand it, minus p1 into log of q1 is 2, minus p2 into log of q2 is 2, minus p3 into log of q3 is 2, minus p4 into log of q4 base 2. This is what you get. And then you substitute the values. P1 is 1. 1 into log of 0.7. Minus. P2 is 0. 0 into anything is 0. 0 into log of 0.1 will be 0. Minus. 0 into log of 0.15 will again be 0. Then minus, again 0. 0 into log of 0.05 base 2. Again that would be 0. So ultimately this go to 0. You get only this. Whatever be that value. So you need to have the data in this way only. 1, 0, 0, 0 for cat, dog, tiger, lion. Even in your original data set, if you have a label called as cat, dog, tiger, lion, etc., you need, what do you need to do? You need to create dummy variable for that. If you create a dummy variable for this, you'll get cat, dog, tiger, lion. If the first image is cat, you'll have a 1 here, rest of will be zeros. If the next one is dog, you'll have 1 against dog, rest all will be zeros. Only if you have your data in one hot encoded format, you can calculate cross entropy. Only in 1000 format, if you have your actual data, only then can you calculate cross entropy. Hence, we are using this one. On similar lines, if you have 0, 1, 2, 3, 4, all that, you are converting that into one hot encoded format. That is, you'll have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If the first number is 0, you'll have 1 here, rest all will be zeros. For the second, if you have, if this is 1, you'll have 1 there, rest all will be zeros. In that way, you have the data set. So if I run this within NumPy utilities, there is an inbuilt function called toCategorical. This toCategorical will create one hot encoded values for your training data output and test data output. So when you run this, within 0 seconds it ran, so it created dummy variables. Let's move on to the next one. Now here what you're doing is you're saying, go to this y test data. When you say dot shape, it will give you the dimensions of the data set. Okay, it will give you the dimensions of the data set. Is this part done? Not yet. It's still doing okay. Let it examine. In the dimension, you'll have number of rows into number of columns. So dot shape will give you the dimensions, wherein it will give you number of rows and number of columns. If I go to show you that, what I'll do is I'll take only this part, I'll run it. Thousand by 10. This has an index number 0, this has an index number 1. If you say y underscore test dot shape, it will give this. Of 1 means it will take this 10. And this number 10 gets stored in this object called number of classes. In number of classes, the 10 would be there. You can look at the shape of all the other variables also. Only the last line is getting executed, right? So let me do one thing. If you want the clean data shape, if you want all 4, right? You just need to say print of this. All the shapes, right? So your training data has a shape of 5,000 observations and 784 columns. Your training data output has 5,000 observations and 10. 10 because it's a 10 class problem. Given a number, you need to classify whether it is 0 or 1 or 2 or 3 numbers. 0 to 9, you have 10. So it's a 10 class problem. So you have the shape of all the observations. And here, number of classes is nothing but 10. You could store that in this object called number of classes. If you just see number of classes, it will say number of classes is 10. Then what you're doing is you're creating a function called as define. In Python, this is how you write your user-defined functions. Not inbuilt functions, but user-defined functions. In this, you're just giving a name, logical name. You're designing multi-layered perceptron MLP and brackets and Cuda. When you enter, there'll be indentation, that additional space. Not the space bar, but maybe the tab. When you click tab, it will come, right? Indentation. You are creating a sequential model, a dummy sequential or empty sequential model. And within that sequential model, you're adding dense layer of 150 neurons, but you're saying input dimension should be 784. Why you have 784 inputs? So you are taking the input layer as 784 because you have 784 inputs. You are connecting those to 150 neurons. I cannot draw 1, 2, 3, 4 circles, right? 150, so I'm drawing in this. So you have some 150 neurons. And you're using ReLU activation function. For each of the neuron, 150 neurons, it will have integration, activation. Activation functions are ReLU. You can try out experiment. We are taking ReLU. It's experimental. You also experiment. Then we are adding another layer to this of 200 neurons. And every neuron has an activation function which is tanh, hyperbolic tangent. Then you are adding another layer of 100 neurons. And every neuron has an activation function tanh. Then you are adding another 500 neurons to it. Another layer wherein you have 500 neurons. And to each and every neuron that you have here, you are using tanh activation function. Then you are adding how many units? Number of classes. Number of classes are 10. So you are adding 10 neurons. Why 10? Because that's the output layer. In input layer, number of inputs that you have is equivalent to number of neurons in input layer. Then here you have 10 neurons. Number of classes in your output is equal to number of neurons in output layer. And you're using softmax activation function here. After you design your architecture, neural network architecture like this, you are then expected to compile the model. Then you use model.compile, and when you compile, you're giving a loss function as categorical cross entropy. You have multiple categories. When you have multiple categories, what is the loss function that we use? Categorical cross entropy. You have output variable which is discrete in more than 2 categories. So you have categorical cross entropy. And when it comes to optimizer, we are using Adam. ADA grad, ADA delta, RMS prop, you can use whatever you want. We are using ADA. And we are saying the metric that we want to use to evaluate your model, to evaluate our model is accuracy. Okay. And then you are saying return the model that we created. This is the function that we created. Now, a few corrections I want to do right away. Best practice, because after you clear your interview, first round, which is going to be verbal interview, they will also give you a data set and a business problem, and they'll ask you to solve the business problem. So here, you have 150 neurons, space. After comma, you need. After comma, it's always advisable to give this. Because when they give you a business problem and give you 1-2 days to solve it, that means you have to write program. They look at the best practice, whether you're following the best practices or not. One best practice is certainly to have after comma have a space, coding best practices. Another thing is having a comment lines. So for each block of code, write these comments, hash, and then what that block does. This space is always good after comma, just to give it a good structure. After equal to, also, it is advisable to give a space. Before and after equal to sign, give a space. That's according to coding best practice. It will look very, very good. You know, earlier we have written, how was it? Now it's looking very professional, right? So, in 0 seconds, this was done. Now, let me add another piece of code. What we shall do is, I take these two and then run. Yeah. So this design MLP, you're storing it in another object called as model, and you're saying model.fit. Fit means you run your model. So you define your sequential model, you compile it, and then now you're fitting it. When you fit, you give your inputs, output, and then number of epochs. Batch size, if you're giving batch size, that means you want mini batch SGD. And number of epochs are 20. Run it. It's going to run different epochs. Let's see how much time it takes. Epoch 1 of 20, 2 of 20. Oh my God, it has taken each epoch only approximately 4 milliseconds. And the initial accuracy was 0.41. And the final accuracy here for the training data is 0.9962. And the loss is also decreasing. Loss is supposed to be minimized. Accuracy has to increase. While loss comes down, accuracy increases. Let me add another piece of code. And then after you feel you built a model, it is always advisable to evaluate a model on the test data. So when you have data, you split that into training data and test data. Then you build your model and test it on the test data. You're building a model, you're on the training data, you're testing it on the test data. Model would evaluate on the test data means it will test on the test data, and also you have the actual values. So when it tests on the test data, you get the predicted values. You're comparing it with the actual values, and verbose equal to 1 means it will show you a line. After it completes the task, it will show you 1 line. Okay, I'll show you that. Then what you're doing is you're saying print accuracy You want exactly this to be on the display. But then when you get the accuracy values, you want the percentage and 3 points after that. If it is 98.786, you want three digits. And you want it in percentage terms. If you want it in percentage terms, what you do is you're storing the results in this evaluation score. Or first, let me run this first. It'll be easier. This is the evaluation score. Verbose equal to 1 means it just gives you 1 line. In this, you have two parts. This has an index number 0, this has an index number 1. So you are going to this object, you're saying of 1 means it will take this, and you're multiplying it with 100. When you take this number and multiply it with 100, you get 94.9. That's your accuracy. If you go to run it, it says 94.9. And you want three floating point values. 1, 2, 3. After decimal. Floating point means decimal. After decimal, you want 3. Then the same thing we shall do on the training data also. So when you use your model and evaluate on the training data, whenever after comma, give a space, absolutely that is going to add to the best practice. And if I were to run it, it does the same thing. Okay, it will save the score, or let me delete it and rerun it. So you run this. So you're evaluating the model that you built on the training data. Verbose equal to 0 means it doesn't give anything. But if I say verbose equal to 1 and then run it, it will run and show you the result. In that way, you also have verbose equal to 2, it will show a status bar. And if at all multiple epochs run, it will also show you the status bar. Okay. Then print. Evaluation score training of 1 means it will refer to this. Of 0, within these square brackets, if you give 0, it is going to refer to this. If you multiply it with 100, 0.9976 multiply it with 100, you get 99.760. That's the percentage. So we could successfully complete the implementation of multi-layered perceptron using your TensorFlow Keras. Will we stop here? Not really. What will we do then? We will get into Pytorch. If we execute in Pytorch, another thing, by opening a new notebook, file, click on new notebook, it will open this. I'm just going to rename this as Pytorch, ANN or MLP or dense network or fully connected network, whatever you need, all that means the same. But now that we are getting started with Pytorch, it makes sense to understand a few things pertaining to Pytorch. Some theory pertaining to Pytorch. After that theory, we will get into the practicals. After the practicals, then we will have to do CNN and RNN also at a superficial level. That would take maybe an additional 4 hours or so. We will figure out, okay, when we need to do that. But let's do one thing. Let us get started into Pytorch discussion. So we need to get into the discussion of Pytorch. A little bit of theory before we get into the practical zone. Pytorch is a library, deep learning library for that case. And it was developed by FAIR. What is FAIR? Facebook's AI research. Okay, and it is free and open source software, and it has approximately 2,000 contributors. It will run. It will help you run. Build. It will help you run and build and run rather dynamic neural networks, and it will perform something called as auto differentiation. Differentiation is nothing but calculus, differentiation, derivatives, and all that. It helps you perform this in Python. And it has GPU accelerators. It supports GPU acceleration. These are all important features required for deep learning research. It is very simple, very flexible. Its interface enables fast experiments, right? You can load the data, you can perform transformations and build the models just with a few lines of code. Just with a few lines of code, you can do the magic. Its ecosystem is becoming very large. Universities such as Stanford is using it. Companies such as Uber, Nvidia, Salesforce, all these have openly told that Pytorch is giving them amazing results. And in 2019, before COVID, 69% of computer vision and pattern recognition proceedings used Pytorch. There is a conference which happens on computer vision and pattern recognition. 69% of the conferences on this was on Pytorch. And then 75% of both, there is something called as ACL, Association of Computational Linguistics, and NAACL, North American chapter of Association for Computational Linguistics, used Pytorch. 50% of International Conference on Learning Representations used Pytorch. Okay. And today, as we speak, you have more than 60,000 repositories on GitHub, which is using Pytorch, related to Pytorch. So the new kit is here. It was made open source. Pytorch was made open source in 2018, while the work on that started in 2017. So it's a relatively newer thing, but it's becoming very popular. And Pytorch is supported by all the major cloud platforms such as AWS, Microsoft Azure, and Google Cloud Platform. All of these use Pytorch. And Ali Cloud, Alibaba Cloud also uses this. Okay, nowadays you have machine learning operations and all that. It works very well. On containers such as Docker, when you have a large scale training, a huge data set to be performed on GPU, it works well. If you want to run Pytorch at scale, today only 100 people are using. Tomorrow, 1,000 people might use my application. Will Pytorch still support? Yes. Pytorch is supported on Google Collab. There is on Kaggle competitions. You have something called as Kaggle kernels, similar to this, similar to what you're seeing. That also supports Pytorch. So Pytorch is very mature and stable today. It can support the GPUs, CPUs, GPUs, and TPUs, tensor processing. And parallel processing is also supported. TPUs are nothing but AI accelerated ASCIIs. ASIC. Application specific integrated circuits. These are nothing but chips, semiconductor chips. And the TPUs are developed by Google. And these are developed by Google because they wanted to give some alternative to GPUs. Pytorch can be used for distributed training. What do you mean by distributed training? If you have 1,000 terabytes of data, you cannot store it on one server because one server might have maybe 100 terabytes storage. So you need 10 different servers. Okay, another 100 terabytes here. In that way, you need 10. Only then you can store 1,000 terabytes. It also supports Pytorch deployment to production. Deployment to production environment. When you want to deploy a model to production environment, it supports. You have something called as Torch script. And you have something called as Torch serve. These are the two features which Pytorch has so that you easily deploy a model into production environment, including the cloud service. Pytorch also supports mobile deployment. You can deploy the models on iOS, that is iPhone, iOS operating system, and Android devices as well. Okay, it has a beautiful ecosystem, amazing ecosystem. In this ecosystem, it has something called as Torch Vision for vision applications. It has fast AI. It has Pytorch Lightning. Which will help support various fields such as computer vision, natural language processing, so on and so forth. Fast AI works, or it's specifically inclined towards natural language processing problems. And it's not just Python interface, it also has C++ interface. Not just that, Pytorch also supports integration with ONNX. What is ONNX? It is a format wherein whatever you use, for example, you might use TensorFlow, or you might use Keras, or you might use Caffe, or you might use Pytorch, whatever be the extension or the format in which the models are saved, all of those are converted into a common format called ONNX, so that they are quite compatible with computer vision applications, OpenCV, etc. So that's, I'm sure we have enough number of reasons on why Pytorch is, becoming extremely famous. Not famous, but it is becoming extremely famous. Okay, now we know about Pytorch, right? I think we should now get started. For that, I'll go here and we have deep learning using Pytorch and TensorFlow. I'll just download Pytorch and I'm going to download the dataset. Let me click on Pytorch and extract the data. Let me also extract the data pertaining to energy data. Okay. Then what I'm going to do now is I am going to open the data set here pertaining to Pytorch, and we will run the lines of code. Hopefully we have time. Hopefully. Okay. And for this also, okay, for GPUs, you need something called as Cuda. I'll do one thing. I'll first copy this. Yeah. If you're installing it on your local machine, what's the status on my local machine? It's still examining 3% done. Okay. Let it fix this issue. While it does, we'll go here. But if you want to install on your local machine, it is pip install torch, pip space install space torch vision. When you run this, it is going to install Pytorch. Okay. Now, in Google Collab, it already has the details. So what we are doing here is I'm going to import. So even before that, we'll have to change the runtime. Let me change the runtime. Click on first manage sessions. You need to terminate the previous session in an MLP. And then I'll go to runtime, click on change runtime type. I'll select GPU and hide on. Let me save it. Okay. Then click on connect. When you click on connect, it's going to connect to your GPU. It's going to allocate, Google is going to allocate computer resources for you to proceed further. Okay. In Pytorch, the allocation of variables to Cuda, which is Compute Unified Device Architecture, it can be done using torch.cuda package. I'll show you that. So first thing is we are going to import Torch. On Google Colab, Torch is already installed. When I hover my mouse and click on code and then paste this, what it does is, what we are doing is rather, we are creating a tensor. You have what? Scalar, which is a single number. Say you have 5, 6, etc. The single number. It's called a scalar. It is zero-dimensional tensor. Tensor is some mathematical concept. Okay? Then you have vector. When it comes to vector, you'll have various values. And vector is one-dimensional tensor. And you have matrix. 1, 2, 3, 4, some matrix. This is called as two-dimensional tensor. Then you have tensor. Tensor has more than 2 dimensions. 3, 4, 5, 6, more than dimensions. Right? But tensor is a basic math calculation. So what we are doing is we are creating a tensor which will be filled with 10 numbers. And these 10 numbers would be filled with some random integers in the range of 0 to 1. That is what this line does. You are creating a tensor which is of more than 2 dimensions of 10 numbers which are randomly generated in the range of 0 to 10. And you're storing that using this equal to or assignment operator into an object called X. By default, it will go into CPU. But if you want to assign this to GPU for computation purpose, you have to say to Cuda. Cuda stands for Compute Unified device architecture, compute unified device architecture. Let me run it. It's assigning to GPU, right? So it's taking some time. But that's okay. It will quickly complete. And then if you want to allocate a variable back to your CPU, so tensor, all these numbers got generated 10 numbers randomly. It is assigned to Cuda of 0 device. That means to a GPU machine. If you assign it to a CPU, look at this device Cuda 0 that didn't appear. It is a good practice to allocate the model holding the network architecture as well as the input data. Okay, to Cuda. It will ensure that all computations during a training process are handled by GPU machine if you assign it to Cuda. Now, you can also determine whether Cuda is available on your computer or not. You can verify first of all. Okay, if it is available, then you can use it. To verify whether you are able to, whether can you allocate your variables to Cuda or not, you can just use this function. Is Cuda available? So you're saying torch.Cuda, is it available? True, it is available. If not, you'll get false. Okay. So simply put, tensors are used to store the data. And when it comes to neural network, it's all about tensor operations. That is why Google called their library as TensorFlow. It's just a mathematical entity which will store your data. Now what we will do is, let us create two tensors, tensor 1 and tensor 2. Just like that, tensors are nothing but some entities, some mathematical entities, that's it. So I'm creating these two. We are creating tensor of 1102. Tensor is some math representation. You're representing the data in some format called as tensor. Okay. Here you're defining a one-dimensional tensor. You have 1102. And here you're creating two-dimensional tensor. Two things. But we are filling it with some random numbers. The first tensor will give you a dimension of 4 because it has 4 numbers. So let me do one thing. If you say tensor 1 of shape, if you run it, it says size is 4, 1, 2, 3, 4. For the second one, it says that you have 1 and 2 dimensions and each one has 5 elements. So if I say tensor 2 dot shape, and if I were to run it, it says 2, 5. It says this is 1. Okay. 1 dimension. This is another dimension. And both of these contain 5 elements each, size of 5. So that's the size, TensorFlow size. If you want to assign it to Cuda, how do you assign it? You just say torch.tensor of these dot Cuda. That means it will assign it to Cuda. Typically, that's how it works. Okay. And creating dummy data using Pytorch tensors is a fairly simple task, similar to what we do usually with NumPy. Within Torch environment, You have something called as rand n. Okay, let me show you that. We have two examples. This rand n will create a tensor which is filled with random numbers with these dimensions. 3, 3 means those dimensions. And also, you have something called as rand int, which generates random integers, wherein you're saying, I want the random integers to be generated of size 3 by 3, which should be in the range of 0 to 2. While you're saying you want integers, on another side, what are you doing? You're saying that I also want to convert the type into floating point values. So you can generate integers and let it remain like that. Or you can take those integers and you want to convert that into float. Typecasting, coercion, converting one type to another. You can, if you don't include this, it will generate integer values. If you say dot float tensor, it will generate float point values. Okay, now that we have some fair bit of understanding, let's look at a few other options. I think we have only a few things. After these, we will get into the first algorithm. Okay. So I'll copy these three and I'll show you what these three. Just a few examples, friends, just to get familiarized with TensorFlow. So what we are doing is we are creating tensors of rank 1, rank 2, rank 3. Rank 1 means 1 dimension. Rank 2 means 2 dimensions, and in each dimension you have 1, 2, 3, 4 elements. 1, 2, 3, 4 elements. And here you're creating 3 dimensions. You're creating 1 dimension of this and this. Another dimension is 1, 2, 1, and 2. Another dimension is the different elements in that. So you're creating 3 dimensions. Rank 3, that is called as. We are using the values in the range of 0 to 1. Okay, to fill the set tensors. So I'll run this. When you just say tensor underscore 1 dot shape, it will give you tensor 1 shape. If you type tensor 2 dot shape, it will give you tensor 2 shape 2, 4, and tensor 3 dot shape. If I go to run it, it will give you tensor 3 shape 2, 2, 2. So you have 2 kind of tables. In that you have 2 rows, and then you have 2 elements in each. That is what it means. Okay, if you want to print everything, then you just use this. The moment you use print, and if you were to run it, it will show you for all 3 guys. That's the difference between print statement and this. Okay, now let me come up with a new cell. If you say dot Cuda, it will assign it to GPUs. And of course, you can type this and see the, the print, the shape we know. When you say torch.size, what does it do? Oh, sorry. Right. So this is what you got here, right? The same thing is given here, I believe. My bad. Let me delete this. And that's not needed. You need not even run that. My bad. Okay. Next thing is this piece of code. I think this is the last piece of code before we get into the use case and solve that particular use case. There are a lot of advantages of Pytorch. You already know speed, ease of use. Each line of code can be executed individually, and you can fix the issues if there are any. You have a lot of pre-trained models as well. Earlier, there was a small community, documentation was not that good. Today, it's a different ballgame altogether. And you have a very important thing called as autograd. Within Pytorch, you have something called as autograd. Autograd library consists of a technique which is called automatic differentiation. Its purpose is to numerically calculate the derivative of a function. It does a back propagation. Your neural network algorithm will come forward, back propagate and update the weights. When it updates the weights, it uses the formula wherein here you'll have differentiation. You differentiate the error into your input. Derivative or gradient is also called as rate of change. So gradients, they refer to the magnitude in which the parameters or weights get updated in the training step, and they get updated to minimize the loss. Right? So it has something called as autograd concept, which does all these things automatically. Of course, it has to do automatically. There's no other way, right? So we are creating, look at this, friends, we are creating two functions. What are we doing? Two tensors are created. We are using this requires grad equal to true to tell Pytorch, okay, to calculate the gradients of that tensor. But then, when building your neural network, that argument is not needed. That argument is not needed. But when you want to calculate the gradients of that tensor, that argument is really needed. And what we are doing here is we are doing a simple addition. We are taking all these two values, we are doing addition. We are adding these two, and then we are squaring them, and then we are adding them. And finally, you are using something called as backward. This is used to calculate the gradients. Now, when you print the gradients of A and B, for B, you did not use required gradients. For A, we have used. So ideally for A, it will not throw any error. For B, it will throw. Look at that. For A, what it has done is, you're adding A plus B, and you're squaring them. That's what you're doing AB. When you say AB dot backward, run until here. Let me remove these two. I'll run these two later. First, let me run this. It executed. Okay. And then, if you just say A dot grad, it will show that yes, there are gradients for it. Okay, gradients are generated. But then if you say print B dot grad, it throws error. Okay, so that's something that you need to remember. Only if you use this requires underscore grad, it will work well. Otherwise, it doesn't. And within TensorFlow, there is a module called as neural network module. Sorry, not TensorFlow, Pytorch. My bad. What am I talking about? Right. Within Pytorch, there is neural network module, NN module. Here you have something called as AutoGrad library. Okay, this AutoGrad library is alone used to build simple neural networks. However, this methodology is cumbersome. If you use only this, a lot of lines of code have to be written. Hence, people came up with NN module, which is far more simpler. NN module is a complete Pytorch module, which is used to create and train your neural networks. Okay, so what we shall do is, I shall go here and we shall start off with this. But for that, I need to copy this energy complete dataset. Okay. We need to copy this and then we need to store this. Will I be able to complete this? I doubt it. So instead of starting this piece of code, what I'll do is I'll talk about some more theory. In Pytorch, there is another package called as Optim package. Okay, there is a package called as Optim. This is used to define the optimizer. Okay, so when it comes to optimizers, you have Adam, stochastic gradient descent, root, mean, square, propagation, prop, RMS prop, so on and so forth. So you can make use of this Optim library. Okay, and then you can run your algorithm. Okay, so that's about your Pytorch. And then what I should really do now is I should probably stop. And then when we connect next week on Saturday, I think that one day would be sufficient for us. Next Saturday is, let me stop this. So I'll stop here and we'll continue the discussion in the next module.